In this video, we are going to look at multiple representations of quadratics, kind of pull together all the things that maybe we know about quadratics, maybe we don't, kind of give ourselves a clean slate for moving forward for the rest of this unit. Okay, so multiple representations, just like when we're talking about lines, we're talking about a situation, a graph, a table, and a rule. So we're going to look at what a quadratic could look like in those four cases. We're going to look at one example kind of throughout those, as well as kind of more general information about them. And so while you don't necessarily know how to move between all of these yet, we're going to look at all of them. Okay, so situation, table, graph, and rule. So first of all, what sort of situations would lead you to a quadratic rule? The biggest one that is talked about most often is projectile motion, meaning whenever something is thrown, or like a rocket launch, or if you kick a ball, those all lead you to a parabolic curve, which is modeled by a quadratic. Along with projectile motion, if you take a cone, right? I don't know if you remember looking at these last year, but if you take a cone and you do a cross section of it, so you like take a slice, right? This should have been something you talked about in 7th grade. So it looks like, here's a cone, and then you take that cross section. That cross section is a parabola. Okay, this is something, there's literally a whole thing in math called conic sections, that if you go far enough and you keep taking math in college, you'll like study this. It's a thing that people look at. And then you'll also see parabolas show up in architecture. So like the Golden Gate Bridge, apparently, like there's arcs on that are perfect parabolas. So geometry, architecture, you can Google it, you can find other things where parabolas and quadratics show up. So for our example today, we are going to look at a hypothetical situation in which someone is testing a rocket. It's kind of a homemade bottle rocket sort of situation. And they're going to light a fuse, and then the rocket is going to shoot straight up in the air or as high as it goes, and then it's going to come back down. And we're going to be graphing the height of that rocket versus time. Okay, so the one that we're going to look at today is going to be height of rocket versus time. Okay, and to do that, we're going to make a table. So the time is going to be the x, and the y is going to be the height, and I'm going to leave a couple empty spots here because eventually we're going to work backwards, but we're going to say that they set that timer at the same time that they start the stopwatch, and then after 2 seconds, that's when the rocket is going to actually leave. Okay, but at 2 seconds exactly, it's still going to be at a height of 0. And then after 3 seconds, it's going to go up to, it's going to be 9 feet tall, 9 feet high in the air. After 4 seconds, it's going to be 16 feet high. And then after 5, it'll be 21. You're copying all this down with me, so you have an example. After 6 feet, it'll be 24. After 7 feet, it'll be 25. And after 8 feet, it starts dropping back, 8 feet, seconds, this is seconds, I'm saying the wrong things. After 8 seconds, we're down to 24. It's reached the top, and now it's starting to come back down again. And then after 9 seconds, it's at 21, etc. Okay, there's a couple patterns I want us to notice in here. So if we start this point right here on our parabola, that would be called the vertex or the maximum. That's the highest point it ever reaches, right? before it turns around and keeps coming back. Now, if we look at this table and we go down, between 24 and 25, that's a 1 foot difference. Between 21 and 24, that's a 3 foot difference. Between 16 and 21, that's a 5 foot difference. 9 and 16, that's a 7 foot difference. 0 and 9, that's a 9 foot difference. What do you notice here? 1, 3, 5, 7, 9. And then the same pattern goes on the other direction. 1, 3, and the same pattern would continue if we continued this table. Okay, that's a really important pattern. All parabolas follow this, except it can look different. So like it's not always 1, 3, 5, 7, 9, but there's always going to be a pattern in those differences. Okay, that's one of the, it won't always be this pattern, but there always will be a pattern in the differences that you can follow that's linear. Okay, how do we write that? We're going to say there is always a linear pattern in the differences. And that's not going to matter super much for this class, but as you go on and continue in your study of quadratics and parabolas, that's going to become more of a big deal. Okay? All right, now, other things we should notice. When y is 0, x is 2, that means this is one of the x-intercepts. With parabolas, for some reason, we also have another word that we use, which is a root. So this is also the root of the parabola. And often there are 2 roots, right? Because parabolas are very symmetrical. In order to find the other root, we would have to continue this table further. Now, parabolas also often have a y-intercept. We don't have a y-intercept for our data here because there's nowhere where x equals 0. But if we worked backwards and we use that pattern, 1, 3, 5, 7, 9, and we could go 11 further down, which would give me negative 11, and then I could go 13 further down, which would give me negative 24. And so that right there, that would be my y-intercept. Now, in this context, that doesn't make sense, right? The rocket didn't start underground. It was at 0 and 0, at 0 and 1, right? Because it was just like the fuse was burning and it was waiting to go. But if we were to graph this, that's where that y-intercept would be. Think about stats, right? Sometimes the y-intercept doesn't make sense, but it's still there and it's still good for us to know what it is because it helps us with the math. Okay, let's go ahead and graph it now. So on the x-axis, remember we're putting seconds or time. And then on the y-axis, we're going to put height. We have to get all the way up to 25, so I'm going to go by 2s. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, so 25 is going to be way up there. Okay, height, and we're saying that this is feet. Great. So now we're going to go ahead and plot the points. I've only included the first quadrant because our domain says that any negative values don't make sense with this context, right? So even though I have some negatives in my table, I'm not going to graph them because they don't make sense with the context. So I'm going to do 2, 0. I'm going to do 3, 9, 4, 16. All right, so I get to here, and my table doesn't have any more data after 9. Oops, after 9 was at 21, but I can tell because of the pattern that 10 would also be at 16, so I'm going to put that there. I can tell that 11 would also be at 9, because that's the next number, so I'm going to put that one in. And I can tell that 12 would be at 0. Right? I can see that because in my graph, those are like the symmetrical points. Okay, so let's go ahead and try and sketch that in. hard to draw a good parabola. Try and not make the chunks connecting the line, the parts straight, right? We don't do straight chunks, we do like a curve. Okay, so this is the trajectory of my rocket for time, right? Seconds up, seconds back down. The important thing to note here is that we have a line of symmetry. I want you to draw that in. You're going to draw in a dashed line going right down at 7. And so we're going to say x equals 7 is the line of symmetry. And we're going to remind ourselves that looking at the graph, the roots are here and here, and the maximum height of the rocket, as well as the maximum point on the graph, as well as the vertex, was at 7.25. My roots were at 12, 0, and 2, 0. And I don't have my y-intercept on here, but I identified it in the table. Okay. Last thing that I said we were going to talk about was a rule. So you don't know how to find a rule for this yet, but I'm going to tell you what it is. The rule for this guy is y equals negative x squared plus 14x minus 24. That's written in standard form. Standard form is y equals ax squared plus bx plus c. That is standard form. And there's also factored form. So to find the factored form of a quadratic, you would ignore the y equals and then you would factor that quadratic. So this one happens to factor to y equals negative x squared. Oops, that's what I just wrote it. Sorry. The factored form is, in parentheses, negative x plus 2 times x minus 12. Ooh, barely squeezing that in there. Negative x plus 2 times x minus 12. And that is just the factored form of this quadratic. You can do it yourself to prove it. I would make you do it, except we're kind of out of time. Okay, practice problem. All right, so for your practice problem, you're going to go on Desmos. You are going to graph this equation, y equals negative x squared plus 17x minus 42. And then I need you to tell me, either as a coordinate for those first three, or as a little equation, where is the minimum or maximum, the y-intercept, the roots, if there are any, maybe one, maybe two, maybe none, and the equation of the line of symmetry. There's definitely a line of symmetry. Okay? So go back, if you've forgotten what any of those terms mean, go back and take a look back in the video. Okay? I'm expecting to see something. I'm expecting to see 4 things from you for this. Okay? You do not need to submit the graph itself, just the coordinates and the equation.